Imagine a command structure facing total industrial exhaustion forced to choose between 10,000 reliable rifles or a single 1,350-ton railway gun requiring a dedicated battalion just to aim. This is the ultimate strategic trade-off. Do you prioritize logistical stability or the desperate pursuit of a singular, decisive blow? When engineering shifts from incremental improvement to the pursuit of the physically impossible, the result is a series of machines that look impressive on a blueprint but fail the moment they encounter real-world friction. This analysis diagnoses 10 specific projects, from the massive Schwerer Gustav to the speculative Haunebu III, through the lens of performance versus practicality. We examine the mechanisms, from volatile rocket fuels to the caffeine-loaded chocolate used to sustain crews, to understand why some provided utility while others remained catastrophic drains on resources. Each entry represents a specific point of engineering hubris where the desire for a wonder weapon ignored the constraints of material science. By stripping away post-war mythology and focusing on technical specifications, we identify the true cost of these designs. A weapon that defies the laws of physics or logistics is not a miracle. It is a liability. We are evaluating the precise moment where innovation crossed into delusion, determining if these projects were breakthroughs or merely expensive distractions. The Schwerer Gustav, later nicknamed Dora, stands as a monument to engineering ambition, a railway gun of unprecedented scale. Its sheer physical presence, defined by an 800mm caliber and a staggering 1,350 tons of weight, immediately signals a departure from conventional artillery. This colossal weapon was conceived with a singular, audacious objective: to breach the formidable French Maginot Line with a single, devastating projectile. The weight alone is comparable to a destroyer ship, underscoring the immense logistical and industrial might required for its creation and deployment. However, the Gustav's theoretical power quickly collided with practical limitations. While its 7-ton projectiles could indeed travel up to 50 kilometers, its accuracy was severely compromised. The reviewer's verdict highlights this critical flaw. It could obliterate a city block, but not a specific building. This inherent imprecision, coupled with an enormous logistical footprint requiring thousands of men and days for assembly, rendered its strategic value questionable. The barrel itself suffered significant wear, necessitating replacement after approximately 300 shots, further complicating its operational readiness. Despite a successful, albeit limited, deployment in the Siege of Sevastopol in 1942, the Gustav's immense size and slow relocation made it vulnerable and strategically inflexible. Ultimately, the Schwerer Gustav represents a profound trade-off between raw destructive potential and achievable tactical utility. Its existence highlights a design philosophy that prioritized overwhelming force over precision, a gamble that proved too costly in terms of resources, logistics, and operational effectiveness. The weapon's ultimate fate, destruction by German forces to prevent capture, underscores its limited lasting impact, a testament to how even the most extreme engineering can falter when practical constraints are ignored. If the Schwerer Gustav was a logistical nightmare bound by rail, the Landkreuzer P. 1500 monster was the attempt to liberate that firepower from the tracks. This design represents the absolute peak of theoretical engineering hubris. Weighing in at a projected 1,500 tons, the monster was not just a tank. It was a self-propelled fortress. To move this massive chassis, designers proposed using 4-man marine diesel engines, the same units found in Type 7 U-boats. These engines were intended to drive a vehicle 42 meters in length, carrying the same 800mm caliber gun found on the Gustav. The sheer scale of the machine required a crew of over 100 personnel just to operate the primary weapon and navigate the terrain. From a diagnostic standpoint, the mechanical requirements for such a platform are physically impossible. The primary mechanism for movement relied on tracks nearly as wide as the entire chassis to distribute the weight. However, even with maximized surface area, the ground pressure would have been catastrophic. In any environment other than reinforced concrete, the 1,500 tons of steel would have simply sunk into the soil, rendering the vehicle a permanent, immobile landmark. Furthermore, the recoil of an 800mm shell is so violent that the design included 4 massive hydraulic supports to stabilize the platform during firing. Without these, the kinetic energy would likely have shattered the drivetrain or flipped the entire structure. The strategic implication of the P-1500 was nil. It lacked any practical mobility, making it a massive, slow-moving target for Allied air superiority. It required a logistical tail longer than most divisions, demanding specialized fuel transport and constant maintenance for the marine engines. It never left the design phase because it ignored the basic laws of physics and material science. While it promised the ultimate mobile siege weapon, the reality was a machine that could not move, could not be hidden, and could not be sustained. It serves as the ultimate diagnostic warning. Scaling up a successful weapon does not guarantee a successful platform. This transition from impractical railguns to physically impossible land cruisers sets the stage for a shift toward smaller, yet equally flawed, tactical innovations. The Krummlauf represents a desperate attempt to force tactical utility onto a platform through sheer mechanical brute force. Designed as a curved barrel attachment for the Schwerer 44, the mechanism utilized centrifugal force to guide projectiles around corners at angles of 30, 45, 60, or 90 degrees. A periscopic sight was integrated to allow the operator to engage targets while remaining behind cover, theoretically solving the problem of urban engagement risks. From a performance diagnostic perspective, the engineering reality was catastrophic. The primary failure point was the material fatigue induced by the extreme stress of forcing a high-velocity projectile to deviate from its linear path. The internal rifling and the attachment itself suffered from rapid degradation, resulting in a functional lifespan of only 160 to 300 shots. Furthermore, the physics of the redirection caused significant projectile deformation. Instead of a stable, lethal round, the Krummlauf frequently caused the bullet to shatter upon exit. This created an unintended shotgun effect, scattering fragments in a wide, unpredictable cone rather than delivering a precise strike. The loss of muzzle velocity and the drastic reduction in accuracy rendered the device largely ineffective beyond very short ranges. The structural integrity of the barrel was also a constant concern, with a high risk of bursting under the pressure of the redirected kinetic energy. The practical value of this innovation was essentially negated by these fundamental flaws. While the concept of shooting around corners offered a clear theoretical advantage in close-quarters combat, the hardware failed to meet the basic requirements of a reliable service weapon. The logistical burden of replacing barrels every few hundred rounds made it a liability rather than an asset. Ultimately, the Krummlauf serves as a cautionary case study in over-engineering a solution where the material limitations of the era could not support the tactical ambition. It highlights the danger of prioritizing a specific combat capability without first verifying that the underlying materials can withstand the operational stresses involved. This failure to account for material fatigue and ballistic stability marks a clear transition from the era of massive, immobile siege weaponry to the increasingly fragile and experimental tactical gear that followed. The ZG-1229 Vampire system presents a stark example of early night vision technology's potential versus its practical limitations. This portable infrared device, designed to be mounted on the STG-44 assault rifle, aimed to grant soldiers the ability to see in complete darkness. Its mechanism relied on an infrared searchlight and a converter, projecting an image onto a screen visible to the operator. The system's total weight, exceeding 20 kilograms when including the rifle, battery pack, and scope, immediately identified it as a significant encumbrance on the battlefield. This considerable mass severely hampered troop mobility, making swift maneuvers or extended patrols exceptionally difficult. The operational performance of the Vampire was further constrained by its limited effective range, which extended only up to 80 meters in total darkness. This narrow operational envelope meant it was primarily useful for very close-quarters engagements or stationary observation. Moreover, the system required an active infrared illuminator, a beacon that could be detected by enemy infrared sensors, thereby negating the element of surprise and potentially revealing the user's position. The battery pack offered approximately 20 minutes of runtime, a critically short duration for sustained combat operations. Consequently, only about 310 units were ever produced, seeing limited deployment primarily on the Eastern Front. The practical value of the ZG-1229 Vampire was thus severely curtailed by its design. While it represented a pioneering effort in combat night vision, its extreme bulk, short operational range, and detectable illumination rendered it a cumbersome and risky tool. Its high weight directly translated to reduced tactical flexibility, a critical drawback in dynamic combat scenarios. The Vampire's legacy is one of technological ambition outstripping practical battlefield application, underscoring the essential balance required between innovative concepts and the physical realities of deployment. This item serves as a critical point in understanding the evolution of specialized combat equipment, highlighting how early advancements often came at the cost of fundamental usability. The Horten Ho 229 represented a bold aerodynamic gamble, an experimental German fighter bomber designed as a flying wing without a classical fuselage or tail. This radical configuration aimed to achieve unprecedented performance, targeting a top speed of 1,000 kilometers per hour. Powered by two Junkers Jumo 004 turbojet engines, the Ho 229 was also distinguished by its construction, utilizing a significant amount of wood and carbon composite materials, which some theorized could offer a degree of radar stealth. It was conceived as part of the ambitious 3x1000 project, aiming for a 1,000-kilometer range, a 1,000-kilometer-per-hour speed, and a 1,000-kilogram payload. The performance implications of this design were significant yet fraught with challenges. The flying wing concept inherently reduced air resistance, theoretically granting it superior speed and range compared to conventional aircraft of its era. Indeed, its design principles foreshadowed modern stealth aircraft, with its influence on the Northrop B-2 Spirit often cited. However, the Ho 229 faced substantial operational hurdles. Its complex and time-consuming construction process was ill-suited for wartime mass production. The Jumo 004 engines suffered from reliability issues, and the inherent stability and control challenges of a tailless flying wing design demanded advanced piloting skills and sophisticated control systems that were still in their infancy. Consequently, it never achieved full operational status, with only a few prototypes ever built. Ultimately, the practical value of the Horten Ho 229 lay less in its direct battlefield impact and more in its conceptual legacy. While its theoretical performance promised dominance, the realities of manufacturing complexity, engine immaturity, and control difficulties prevented its widespread deployment. It stands as a testament to visionary engineering that outstripped the technological capabilities of its time, a compelling case study of how groundbreaking design, despite its flaws, can profoundly shape future aviation. Its existence highlights the constant tension between theoretical advantage and practical feasibility in military development. The V-2 rocket, technically designated the A-4, represented a pivot from aerodynamic flight to pure ballistic force. Standing 14 meters tall and weighing 12.5 tons, the vehicle relied on a liquid propellant engine fueled by a volatile mixture of ethanol and liquid oxygen. This mechanism propelled the rocket to a maximum speed of 5,800 kilometers per hour, allowing it to reach altitudes of 100 kilometers. By crossing the Kármán line, it became the first man-made object to enter the edge of space. It carried a 1,000-kilogram high-explosive warhead over a range of 300 kilometers, utilizing a sophisticated internal guidance system comprised of gyroscopes and an early analog autopilot. From a performance diagnostic perspective, the V-2 was a study in extreme trade-offs. Its primary advantage was its total lack of interceptability. Traveling at several times the speed of sound, it arrived without warning, rendering contemporary air defenses useless. However, this tactical invincibility was offset by a critical lack of accuracy. The gyroscope-based guidance was pioneering but imprecise, often resulting in impact points miles away from the intended target. Additionally, the manufacturing requirements were staggering. Each unit required immense quantities of alcohol distilled from food crops and specialized materials, making the cost-to-damage ratio highly inefficient compared to conventional bombing campaigns. The practical utility of the V-2 was ultimately psychological rather than strategic. As a weapon of terror, it could strike London or Antwerp with impunity, but it lacked the precision to destroy specific military infrastructure. It was a resource-intensive project that diverted vital engineering talent and materials away from more sustainable defensive needs. Despite these tactical shortcomings, the V-2's legacy is undeniable. It served as the direct technological ancestor to the intercontinental ballistic missiles of the Cold War and the Saturn V rockets of the Apollo program. While it failed to alter the outcome of the conflict for which it was built, it successfully established the mechanical framework for the space age, proving that the leap from tactical failure to global transformation is often a matter of perspective. The Messerschmitt Me 163 Komet represented a radical departure in aircraft design, a rocket-powered interceptor promising unparalleled speed. This design, however, embodied a critical high-stakes trade-off: extreme performance at the cost of operational viability and pilot safety. The key specifications reveal this inherent conflict. Capable of speeds approaching 1,000 kilometers per hour and an extraordinary climb rate, the Komet was designed to be an uninterceptable threat. However, this blistering performance was sustained for only about 8 minutes of engine runtime. Once its highly volatile bipropellant fuels, T-Stoff and C-Stoff, were exhausted, the aircraft became an unpowered glider. These fuels were notoriously corrosive and explosive, posing a constant, severe hazard to ground crews and pilots alike, often leading to catastrophic accidents even before takeoff. The Komet's operational cycle further compounded these dangers, requiring a jettisonable dolly for takeoff and a perilous unpowered landing on a retractable skid, which frequently resulted in crashes or further fuel-related incidents. The corrosive nature of the fuels meant even minor leaks could cause severe burns or structural damage, making maintenance a constant, risky endeavor. From a performance diagnostic standpoint, the Me 163 was a technological marvel that ultimately failed to translate into effective combat utility. Its limited powered endurance made it difficult to engage targets effectively, as its high speed often overshot slower bomber formations, leaving pilots with only 1 or 2 passes. The overwhelming operational risks meant more pilots perished in accidents than were lost in air-to-air combat. This extreme imbalance between theoretical capability and practical, safe application highlights a critical design flaw: a weapon system that is more dangerous to its own operators than to the enemy it was designed to fight, thus rendering its advanced technology strategically inert. It exemplifies how pushing performance boundaries without addressing fundamental safety and logistical challenges can undermine an entire project, regardless of its raw potential. The Goliath, designated as the SD, KFZ 302 and 303, represents a foundational, albeit flawed, attempt at remote-controlled warfare. This tracked mine system was engineered to deliver a payload of 60 to 100 kilograms of high explosives directly into enemy fortifications or armored concentrations. The unit relied on a physical 650-meter cable to transmit steering commands and detonation signals. Mechanically, the system was split between an early, quiet electric variant and a later, more cost-effective petrol-powered model. These units operated at a sluggish speed of 6 to 10 kilometers per hour, a velocity profile that dictated their entire tactical utility or lack thereof. From a performance diagnostic perspective, the Goliath's reliance on a physical tether was its primary failure point. While the electric motor offered a stealth advantage, the operational reality was dictated by the cable's extreme vulnerability. On a chaotic battlefield, the control wire was easily severed by artillery fire, debris, or simple terrain obstacles, instantly neutralizing the asset. Furthermore, the low ground speed meant that even if the cable remained intact, the Goliath was a predictable, slow-moving target for any infantry unit with basic anti-tank capability. The high production volume of over 7,000 units suggests a desperate attempt to achieve scale, yet this mass production failed to compensate for the fundamental lack of survivability. The system became more of a logistical burden than a tactical solution, as the high cost of each unit rarely translated into a successful detonation against a hardened target. Practically, the Goliath serves as a cautionary study in early robotic limitations. It highlights the critical trade-off between remote-controlled reach and the fragility of the communication link. While it is often cited as a distant ancestor to modern explosive ordnance disposal robots, the Goliath lacked the agility, sensor feedback, and robust connectivity required for true combat efficacy. It remains a definitive example of how engineering a weapon for a specific narrow task, without accounting for the unpredictable variables of the field, leads to a high-cost, single-use system that is easily defeated by the very environment it was intended to dominate. This failure to bridge the gap between design intent and operational reliability effectively relegated the Goliath to a historical curiosity rather than a viable battlefield tool. The Coca-Cola presents a fascinating contrast, not in its engineering complexity, but in its simple, enduring success. Unlike the colossal failures of super-heavy tanks or experimental aircraft, this energy-boosting chocolate bar, introduced for the 1936 Berlin Olympics, achieved its objective with remarkable efficiency. Its core mechanism relies on a high caffeine content derived from chocolate, coffee, and cola nuts. This ingredient profile was specifically formulated to enhance alertness and concentration, making it a valuable tool for pilots and soldiers operating under demanding conditions. While popular lore sometimes conflates it with panzer chocolate, a term often associated with Pervidin, Coca-Cola's success stems from a less illicit, more conventional stimulant. The performance implication is straightforward. It provided a tangible, albeit temporary, cognitive boost. This wasn't about achieving impossible speeds or overwhelming firepower, but about sustained focus. For air crews navigating long sorties or ground troops enduring extended patrols, a reliable method to combat fatigue was a significant operational advantage. The practical value lies in its longevity and continued relevance. Unlike many wartime innovations that faded into obscurity, Coca-Cola remains in production today, a testament to its well-executed concept. Its characteristic round tin and potent blend have cultivated a loyal following, demonstrating that sometimes, the most effective technological solutions are those that directly address a fundamental human need with a well-balanced, proven approach. This product's success underscores that innovation isn't always about radical leaps. It can also be about refining existing concepts to meet specific performance demands with practical, accessible utility. The Haunebu III represents the absolute terminal point of wartime engineering speculation, moving entirely beyond the realm of physics into the territory of modern folklore. Its theoretical specifications describe a massive, 70-meter diameter disc-shaped craft powered by a propulsion system utilizing gyroscopic rings to generate anti-gravity. According to these unsubstantiated claims, the vehicle was designed to carry a crew of 32 people and achieve atmospheric speeds of Mach 10. These figures suggest a level of energy density and structural resilience that far exceeded any material science available in the 1940s. From a diagnostic perspective, the performance implications of such a craft are catastrophic. At Mach 10 within the lower atmosphere, the thermal loads on a disc-shaped airframe would cause immediate structural failure and vaporization of the outer hull. Furthermore, the mechanism of anti-gravity via gyroscopic rings lacks any basis in established gravitational theory or electromagnetism. While the project is often linked to the Skoda factories in Prague or secret installations in the Owl Mountains, there is zero archival evidence that a functional prototype was ever constructed, let alone flight tested. The leap from conventional aerodynamics to speculative energy sources represents a total abandonment of the iterative engineering process seen in contemporary jet and rocket programs. The practical value of the Haunebu III exists solely as a case study in the power of myth-making over technical reality. In a strategic context, these designs served no functional purpose during the conflict, as they remained confined to speculative literature and post-war conspiracy theories. Its legacy is not one of aerospace advancement but of the psychological need to imagine a wonder weapon capable of defying the laws of nature when conventional means failed. By comparing the Haunebu to the actual, flawed successes like the V2 or the Me-163, we see the clear boundary between desperate innovation and pure fantasy. It stands as the ultimate diagnostic failure, a machine that solves every tactical problem on paper by ignoring every physical constraint in reality, forcing a final reckoning with the true cost of these engineering obsessions. The strategic choice between practical, scalable solutions and the pursuit of impossible technological leaps ultimately defined the operational effectiveness of these projects. From the logistical nightmares of super-heavy artillery to the material failures of curved barrels, and the sheer fantasy of anti-gravity craft, the diagnostic pattern is clear. These wonder weapons often consumed disproportionate resources for negligible or non-existent returns. Engineering divorced from reality creates liabilities, not breakthroughs. True innovation thrives not on defying physics, but on mastering its constraints. The lesson remains: prioritize reliable, adaptable solutions over the seductive, yet ultimately destructive, allure of the impossible.